The last section in this chapter is polarity, and to determine the polarity, you need to draw the shape. So, what is polarity? Polarity is the motion of the electrons in the structure. So, it shows you how the electrons are moving in the structure, and it's determined by the electronegativity. See, electronegativity, as we mentioned earlier, it increases from left to right in a period and from bottom to top in a group. Okay, you can have your periodic table next to you. So if I am looking at a chlorine versus an oxygen versus a nitrogen versus a carbon, all of these, they belong to the second period. And carbon is going to be the least electronegative in there. Chlorine is the most electronegative. So by the term electronegative, electronegative means the ability of the atom to pull electrons. So chlorine has an ability to pull electrons towards itself. Let's have an example. So if I have a hydrogen and it's connected to the chlorine, this is hydrochloric acid. Okay. Um, Chlorine is electronegative. Chlorine is more electronegative than the hydrogen. So the chlorine is going to come, it's going to pull electrons from the hydrogen in there. So you can easily see the motion of electrons. It's going from the hydrogen to the chlorine. So it's making simply the chlorine being rich in electrons because the chlorine is kind of like stealing the electrons of the hydrogen. So the chlorine is going to be rich in electrons, and we represent this by partial negative. And the hydrogen will lack electrons because the chlorine took its electrons. So that is going to be partial positive in there. A plus is a sign of deficiency in the electrons, and negative is a sign of having more electrons. So this is called the direction of polarization, which is shown as the direction of the motion of the electron. So it's going towards the chlorine in there. Okay. So the direction of the motion of the electrons is explained by the dipole moment, which we call it mu like that. This is called the dipole moment. And the dipole moment is the sum of all of these vectors. So HCl has only one vector in there. So if you see like there's a motion of electrons, then we say that the dipole moment is different than zero. And if the dipole moment is different than zero, then we would say that the molecule is supposed to be polar. So here we say that the molecule is polar. On the other hand, if the arrows cancel out, this means that I do have more than one arrow in here. All of them cancel out, then the dipole moment is going to be equal to zero. There will be no motion of electrons. Then I would say that the molecule is non-polar. How to determine this? You need to have the molecular shape drawn in front of you and then do the direction of polarization and see, do the arrows cancel out or they don't. We'll have an example on this. But before having an example, let's talk a little bit about the types of bonds. We said that we have two types of bonds. We have an ionic bond and we do have a covalent bond. So these are the types of bonds in there. Now, bonds can be either polar or can be nonpolar. Polar means that, I mean, this is the polarity over here. So polar means that your polar is here. So you have the motion of electrons in the molecule. And nonpolar means that there is no motion of electrons. So covalent bonds can be either polar or nonpolar. That depends on the difference in the electronegativity. Delta En is the difference in the electronegativity in there. This table, you can have it in the exam. And this trend over here also, you can have it in the exam. Let's write it out. So if the difference in the electronegativity is less than 0.5, then we would say that the bond is going to be a non-polar covalent bond. Okay? And if the difference in the electronegativity is between 0.5 and less than or equal to 1.9, then we would say that the bond is going to be a polar covalent bond. And then if the difference in the electronegativity is more than 1.9, then I would say that I'm working with an ionic bond. Guys, this is another way to check if you have an ionic bond or a covalent bond. But I honestly, I prefer to apply the rules that I told you about the ionic bond. These are between metals and nonmetals. Covalent bonds, it's between two nonmetals. Okay. This is the table of the electronegativity. You see the electronegativity values in there. So lithium electronegativity is 1, and you can see the electronegativity increases as you go further to the right of the periodic table. So oxygen has an electronegativity of 3.5. Fluorine has an electronegativity of even more, which is 4 in there. Noble gases are inert. Okay. So let's say, for example, if I want to find the electronegativity of the oxygen fluorine bond. So if I have an oxygen and a fluorine bond in there, and I want to find the type of bond between oxygen and the fluorine. So what you do is you calculate the difference in the electronegativity and you put it in absolute value, you guys. The difference in electronegativity is always positive. So I'm just going to go ahead and put it in absolute value so that the answer that I'm going to get is always positive, not negative. So I'm going to calculate the electronegativity of the oxygen minus that of the fluorine. Let's do fluorine minus oxygen because fluorine is bigger than oxygen. So I would do 4.0 minus a 3.5 in there. So delta E, it's going to be, in this case, 0.5, right? So it's going to be 0.5. So if you come over here and you say, okay, delta E is 0.5, so I would say that the bond between the oxygen and the fluorine is going to be a polar covalent bond. Okay, so that's going to be, the 0.5 is not less than 0.5, so I'm just going to consider it as 0.5 here. So it's going to be a polar and a covalent bond. So the question here, we already reached and drew the geometry and the shape. This is the geometry and the shape of ammonia, of NH3. So you do all the steps. You calculate your valence electrons, you draw the lowest structure, and then after you draw the lowest structure, find the static number as we did earlier. And once you find the static number, go to the Vasper table, get the geometry, the shape, draw it over here. We're here now. So if I ask you about the polarity of the structure, if the structure is polar or not. So this question is, draw the molecule, the ammonia molecule, and see, is ammonia polar or nonpolar? So does it have a dipole moment? So go ahead and draw the shape for the structure. And then after you draw the shape, we're going to go ahead and determine the electronegativity. Remember that the electronegativity, let's put it in orange, electronegativity increases from left to right in a period and from bottom to top in a group. So I'm going to go ahead and draw the direction of polarization. Nitrogen is more electronegative than hydrogen. Nitrogen is more electronegative than hydrogen. Think about this. Nitrogen is taking the electrons away from the hydrogen. So this is the motion of the electrons. Everything is going towards the nitrogen. Everything is going towards the nitrogen. I don't have any arrow canceling out. So everything is going towards the nitrogen. It's going to continue upwards. It's going to continue. So the resultant of all of these vectors, it's going to be upward. So I would say that the dipole moment here is different than zero. That is different than zero, then I would say that the molecule is polar. Now the question is, what type of bonds do I have here between the nitrogen and the hydrogen? I know that they are covalent, but are they polar or nonpolar? So to do this, you're going to calculate the change in the electronegativity. It's delta En, change in the electronegativity. So you look at the electronegativity table. Hydrogen is 2.1, nitrogen is a 3. So you do absolute value of 3 minus 2.1, and that is equal to 0.9. You go up there and you say, okay, 0.9 is between these two numbers in here, so it is going to be a polar covalent. So the bonds between the nitrogen and the hydrogen are polar covalent bonds. So I would say that the bonds are polar covalent bonds. Okay, Let's have another example over here, pH 3. So again, you are given pH 3. You go ahead, you draw its calculate your valence electrons, draw the lowest structure, static number, and then go ahead and draw the shape of the molecule. After you do this, we're going to draw the direction of polarization, right? So phosphorus, hydrogen, I mean, you can look at the table in here. You can see phosphorus is here, hydrogen is here. So phosphorus is more electronegative. Phosphorus is going to take electrons from the hydrogen. So your arrow is going to be from the hydrogen to the phosphorus. So it's going to be like that. And it's going to be like that. So from the hydrogen to the phosphorus in there. Okay? So your resultant vector is going to be pointing up. Nothing is going to cancel. So I would say that the dipole moment is different than zero. The molecule is polar. What type of bonds are there between the phosphorus and the hydrogen? Go ahead and do the change in the electronegativity, 2.1 minus 2.1, because both are 2.1s. This is zero. So electronegativity is zero. This is, let's see. So the electronegativity is zero. Zero is less than 0.5. So I'm expected to be a nonpolar covalent bond. Okay. More examples, OF2 in there. So you just go ahead and you determine the shape. The shape is bent. Guys, as you can see, you cannot determine the polarity if you don't have the shape. So make sure that you have the shape and then determine the polarity of the structure. So for oxygen and fluorine, fluorine is more electronegative. So see, the pull of electrons is towards the fluorine, the pull of electrons is towards the fluorine in there. Fluorines are the you can easily see that the arrows in there, they don't cancel out because the resultant is coming this way, so they don't cancel out. And because they don't cancel out, then the direction of polarization here is going to be different than zero. And I would say that the molecule is going to be a polar molecule in here. The type of bond between the oxygen and the fluorine, you can go ahead and figure it out. Between oxygen and fluorine, this is 0.5. So we said that this one is going to be a polar and it is going to be a covalent bond. Now, for diatoms, you don't have a direction of polarization in there because one of the fluorines will pull this way, the other fluorine will pull another way, so the arrows are going to cancel out. So for all of these diatoms, the dipole moment is equal to zero, so these are going to be non-polar. So all of them are going to be non-polar. XeF4, we can go ahead and calculate the valence electrons and let's calculate the static number. It's 6, geometry octahedral square planar. Look at the Vasper table in there. And the square planar, we're going to draw it like this. All the fluorines are the same. So we're going to draw the fluorine. So you're going to have a fluorine here and a fluorine there, and then another fluorine here and another fluorine there. Okay. And we're going to draw the direction of polarization. So fluorine is more electronegative than xenon. Fluorine is more electronegative than xenon, you guys. Fluorine is an electronegative element. Xenon is not an xenon is inert. Okay. So look here. Those two have a resultant pointing up. Okay. So those two have a resultant pointing up. And then those two over here has a resultant pointing down. The fluorines are the same, so the pull is going to be the same. The pull up is going to be similar to the pull down. So I would say that the dipole moment here is going to cancel. Arrows are going to cancel, so it's going to be zero. So the molecule is going to be nonpolar. Okay. Let's have another example over here. This one we can draw it in two different. Actually, it's going to be the same shape, square planar. So this one is going to be square planar. This is xenon, and you have chlorine. Chlorine. You do have actually one of the chlorines here needs to be in front. And then I have another fluorine in here. can just draw it anywhere you want and another fluorine in there. I mean, I can have the fluorines on one side, I can have the chlorines on one side, or I can have a fluorine, chlorine, and another fluorine, chlorine if I want. This is one of the possible ways to draw this structure over here. Okay. This is I think I missed the two lone pairs because the shape is going to be a square, a planar. Okay, in there. This is the shape. It's a square planar. So if I draw it this way, then this is the direction of polarization. Chlorine is more electronegative than xenon. So for these two chlorines, the resultant is going this way. Okay. And for the fluorines, here you go. So I do have the two fluorines, and the resultant is going this way. Which one is more electronegative? I should make this arrow smaller, you know. So this arrow is going to be smaller because chlorine is less electronegative than fluorine. And then I do have my fluorine, which is more electronegative. So notice these two, they don't cancel each other. Because if all of the groups were the same kind, let's say if all of them were fluorine, as in this example over here, because these two have a resultant going this way, these two have a resultant going this way. The fluorines are the same, so the pull is going to be the same. That's why they cancel. These they don't cancel because the fluorine is more electronegative than the chlorine. So I would say that the dipole moment here is going to be different than zero, so the molecule is going to be polar. Okay, now let's say if I go ahead and draw the xenon like that, and I draw one to be chlorine, the other one to be fluorine here, and one to be chlorine over here, and the other one to be fluorine over there. Okay, so I mix the chlorine and the fluorine. This is another possible way of drawing this structure. Then I would go, okay, I would say that this is here chlorine. This is fluorine. Fluorine is more electronegative. So this fluorine is more electronegative than chlorine. And then I do have a chlorine. I do have a fluorine. So I would say over here that the resultant for these two. So the resultant for these two is simply pointing upwards. Where did it go? The resultant for these two is pointing upwards. The resultant for these two is pointing downwards. Still, fluorine is more electronegative than chlorine, so the pull is going to be different. So I would say that the dipole moment here is going to also be different than zero, and the molecule is going to be polar. So to sum up, you guys, when you determine the polarity of a molecule, you need to have the shape in front of you, and you need to have the electronegativity table to know that which atom is more electronegative, and then go ahead and draw the direction of the pull of the electrons towards the most electronegative element, and see if the arrows cancel or not. If the arrows cancel, then your molecule is not going to be polar. If the direction of polarization they do not cancel, then the molecule is going to be polar, and the dipole moment is going to be different than zero.